Hello everyone and welcome to Modern Software Development and IT from Code to Cloud, the show where we unpack the evolution of how software is built, deployed and scaled. My name is Kalendarova and I'll be your host for this series. In this first episode, we'll be deep diving into two pillars of modern software architecture, microservices and containers. Whether you're a developer, an aspiring engineer or a curious tech enthusiast, this episode will give you both the foundational concepts and the technical depth you need.
Hi everyone, my name is Hristo Stoychev, your tech host for today. As a cloud architect, DevOps and Kubernetes expert, I'm excited to break down these complex topics and make them accessible for everyone. As Maria mentioned, in today's episode, we'll provide a high-level overview of two key foundations of modern software architecture, microservices and containerization. If some parts feel a bit fast or you want more detail, check out my blog articles, links in description.
In short, Hristo, what is the story of modern software development and IT operations?
Modern software development has evolved from slow, hardware-dependent systems to fast, flexible, cloud-native architectures that enables a rapid deployment, which from monthly releases to continuous delivery, global scale, instant worldwide distribution and scaling, cost efficiency, pay-per-use instead of massive upfront investments, and resilience, which is the fault-tolerant, self-healing systems. And the last one, innovation speed, faster time to market and development. In a nutshell, cloud-native architecture is a modern approach to build and running scalable applications in dynamic environments such as public, private, and hybrid clouds. It adopts cloud services, automation, and microservices to deliver resilient and flexible systems. In today's episodes, we'll look at architecture and deployment in present technologies.
So, let's start with the basics. What exactly is a monolithic architecture and why do developers find it challenging?
Let me start with our hospital analogy. Then we'll get technical. In the monolith, imagine a single doctor trying to handle everything: emergency care, surgery, pharmacy, billing, all in one room. Overwhelming, inefficient, and if that doctor gets sick, patient's care completely stops. In Airbnb, our example, and built as monolith application stack, think of Airbnb's single huge application where everything is as one code, handling everything: user authentication, property entries, search, bookings, payments, messaging, customer support, and more. All these features were tightly packed into one monolithic system. A change in one part, like updating the booking service logic, could unintentionally break search or messaging, for example. Deployments were risky, testing was slow, and scaling specific features independently was nearly impossible. Just like one sick doctor holds the hospital, a single bug could bring the whole Airbnb platform down. In microservices, imagine specialized departments for emergency, cardiology, pharmacy, each with expert staff and equipment. Patients move between departments as needed. Each department can scale independently during busy periods, for example, and if one department has issues, others continue operating. Now imagine Airbnb rebuilt with microservices. Instead of one massive code base, each core function is its own specialized service. User authentication, property entries, search, booking, payments, and messaging, all developed, deployed, and scaled independently. Each team owns its service, just like departments in a hospital. If the messaging service goes down, users can still search for listings or make bookings. Teams can update or scale individual services without affecting the rest of the platform. This separation improves reliability, development speed, and operational resilience. Exactly what a growing global platform like Airbnb needs.
So, in technical terms, the monolithic version bundles everything together, but microservices break each function into independent services?
Exactly. Microservices architecture decomposes a large application into a smaller, independent services that communicate over a well-defined APIs. Each service handles a specific business capability and can be developed, deployed, and scaled independently. They communicate over well-defined APIs, as we said, which are sets of rules that allow different software entries to interact with each other. Let me follow the Airbnb architecture example. Instead of one massive application, they have separate services such as booking service, which handles the reservation, host management system that manages property entries, messaging engine that handles communication, payment service that processes transactions, search service that handles property discovery, and each service can use different technologies. The booking service might use PostgreSQL for transactions, while the messaging service uses MongoDB for flexible chat data. One crucial component I must mention here is that you need an API gateway as your single entry point. Think of it as the hospital front desk that routes requests to the right departments. Instead of mobile apps calling 6 different services directly, they call one gateway that handles routing and request aggregation, ensuring smooth and efficient communication.
But this sounds more complex than a monolith. What makes this complexity worthwhile?
Great question. The complexity was already there. It was just hidden inside the monolith. Now it's explicit and manageable. We had a project for a trading platform where a simple algorithm updated regularly, taking down their entire system. After breaking it into microservices, they could update that one service independently. When traffic spikes 10 times during the market volatility, they scale just the trade execution service while keeping everything else at normal capacity. In summary, the key benefits are independent scaling, scale only when it's needed, faster development cycles, teams works independently, better fault isolation, one failure doesn't kill everything, technology diversity, choose the right tool for each job, and in everything we said, I follow the single responsibility principle at the service level, which each service should have one reason to change. The payment service and booking service have different data models, performance requirements, and regulatory constraints. They should be separated. Data ownership is crucial as well. Each service owns its data completely. The booking service has its own PostgreSQL database, separate from the user authentication service. This prevents the tight coupling that often caused issues in monolithic systems.
But it's not all sunshine and rainbows, right?
Absolutely not. Martin Fowler has a great rule. You shouldn't start with microservices unless you have a system that's too complex to manage as a monolith. My rule of thumb is that teams under 8 developers should stick with the monoliths. The coordination overhead isn't worth it. Distributed system challenges are particularly tricky.
Now, let's dive a little bit deeper into how microservices actually communicate. This seems like one of the most complex aspects so far.
You're right. Communication patterns make or break microservices architectures. There are two fundamental models, synchronous and asynchronous. Synchronous communication is like phone call. The client sends a request and waits for a response. It is easy to implement and debug with intuitive code flow. REST APIs and gRPCs are common examples. REST APIs is using standardized software communication protocol like API over internet using HTTP methods. But synchronous communication isn't resilient. If one service is down, the whole chain breaks.
So you're basically telling me that asynchronous is better for resilience.
Exactly. As asynchronous communication is like sending email, you send a message and you don't wait for immediate response. The client typically sends to a message broker, not directly to the destination service. Message brokers like RabbitMQ, Redis, and Apache Kafka ensure that messages are stored and forwarded to the appropriate service, even if the service is temporarily down. Message brokers are the backbone of modern communication systems. There are several different message brokers, each designed for specific use cases and environments. For example, RabbitMQ is excellent for complex routing, high availability and reliability. Redis is lightweight, in memory, great for speed but limited persistence. Apache Kafka is the powerhouse for high volume event streaming, and Azure Service Bus is a cloud managed messaging service using queues and topics, for example.
Can you give us maybe a practical example of when to use each?
Sure. For our Airbnb example, Synchronous is a REST API. When the booking service needs to verify payment immediately for real-time confirmation. Asynchronous is like Azure Service Bus. When a booking is completed, triggering multiple actions like sending confirmation emails, notifying the host, and updating recommendations. RabbitMQ for complex routing scenarios where messages need to be different services based on the content or priority. And Redis for real-time features like chat messages or live notifications, where the speed is more important than guaranteed delivery. The key here is matching the communication pattern to your business requirements, of course. Critical path operations might need synchronous calls, while background processing works great with asynchronous patterns here.
So far, we have established that microservices give us flexible architecture, but how do we deploy and how do we manage all these services? Is this where the containers come in?
Exactly. Before containers, deploying software was like moving to a new apartment. You pack everything up, move it, then spend 2 weeks figuring out why nothing works the same way. But it worked on my machine, became on every developer's nightmare. I remember once an incident where a critical service failed in production because the production server had a different version of the C library. That's where I became a true believer in containerization.
What exactly are the containers and how do they solve this problem?
Think of containers like shipping containers. Traditional deployments was like shipping loose items in a truck. Your application files, dependencies, and configuration would get mixed up or lost. Containers are like standardized shipping containers. Everything is packaged together, sealed, and guaranteed to arrive exactly as sent. Technically, containers packaged your application with everything it needs, as we mentioned: the code, runtime, system tools, libraries, and settings. They use features like namespaces for isolation, C groups for resource control, and union file system for efficient storage. The efficiency is remarkable. Here, a virtual machine, for example, might use around 2 gigabytes just for the operating system, while a container uses maybe 50 megabytes. Virtual machine boot time is around 30 seconds or more, and containers start in less than 3 seconds.
In your blog, you have mentioned 3 key properties. Can you explain to us what ephemeral, idempotent, and immutable mean?
These 3 properties are fundamental to how containers enable scaling. Ephemeral means that containers are designed to be short-lived and easily replaceable. Idempotent means that operations on containers produce the same result no matter how many times they are performed, ensuring consistency. And immutable means that once created, containers don't change. Any updates results in new container being deployed create predictable, stable environments.
How does Docker fit into this picture?
Containerization was mainstreamed by Docker and created an entire ecosystem. Docker have several major products in their portfolio, such as Dockerfile, which is a recipe for building container images. Every step is versioned and reproducible. They have Docker Hub, which is their public registry for software distribution. Instead of complex installation guides, you can just execute Docker run in your hub. Docker Compose is another Docker product which defines multi-container application in simple configuration files. And Docker Swarm. This is their native clustering and orchestration solution, enabling high availability and balancing and load balancing, and service discovery. But the real magic happens with the orchestration platforms like Kubernetes. Kubernetes treats containers as a first-class citizens and provides declarative management, container scheduling and networking, load balancing, and health checks, auto-scaling based on metrics.
Okay, but let's talk a little bit about the technical architecture. How do containers communicate?
Sure thing. Container networking in the context of Docker has several models. The bridge network, which is the default Docker network model, gives containers private IPs on an internal network. Host network shares the host network stack, improving the performance but removing the isolation. And overlay network allows containers on different hosts to communicate, which is essential for distributed systems. For storage, we use volumes to provide writable file systems. Since containers images are read-only by design, the immutable part, volumes and writable layer for data that needs to persist is on those volumes.
What about container registries and image management?
Container registries are like version control for your packaged applications. Docker Hub is the public option, as we said, but enterprises typically use private registries like Azure Container Registry for security and compliance. Multi-architecture images automatically select the right version for your platform, whether it's AMD or ARM or other different operating system. And Stacks lets you version your images.
Let's go forward with the infrastructure that actually makes all of this possible. What are the core components beyond just containers and services?
Modern microservices architecture requires several infrastructure components working together. The first one is a service mesh. probably the most important modern addition. It manages how different parts of your application communicate with each other, handles security, and provides observability without changing your application code. Istio, Linkerd, and Cilium are popular choices here as a service mesh tools. Configuration management becomes crucial as well when we have dozens of services. Tools like Console, etcd, or cloud native solution centralized configurations across all services as well. Monitoring and logging in distributed systems is completely different from monoliths. You need distributed tracing to follow a request across multiple services, metrics collection for performance, monitoring log aggregation since logs are scattered across many containers. And here are some great examples. Could be Prometheus, which is a great parametrics, Jaeger and Zipkin for tracing, and Elastic Stack, such as also Splunk for logging. We should mention cloud vendor solutions such as Azure Monitor and a cross-platform service like Datadog, but there are many more other.
But how does Kubernetes fit into all that ecosystem?
Kubernetes is the orchestration platform that ties everything together. It provides declarative management, which describe what you want, and Kubernetes make it happen. Pod scheduling, which is the automatically placed containers on appropriate nodes. We have service discovery. Services can find each other automatically. We have load balancing, which is the distributed traffic across health instances. And we have auto-scaling, which provides the scale of the application based on the CPU, memory, or other metrics. And the final one is the rolling updates. Deploy new versions without downtime, particularly. But Kubernetes has a learning curve. I always recommend master Docker first, then move to Kubernetes when you need orchestration. Another important piece are CI/CD pipelines. They have become essential with microservices. Each service needs its own deployment pipeline, but they all follow similar patterns like build, test, package into containers, deploy to staging, run integration test, deploy to production when everything's ready.
So, how do microservices and containers work together in practice?
This is where the real magic happens. Microservices gave us the architecture, containers gave us the deployment mechanism. Containers package each microservices with everything it needs to run, ensuring that it works the same way in development, testing, and production environments. Each microservice gets its own container, solving several problems simultaneously. We have isolation, which is the service can't interfere with each other. We have portability, deploying anywhere that supports containerization. We have scalability, scale individual service by spinning up more containers, and development velocity. Teams work independently with their own tech stacks. Companies like Uber handle millions of rides daily through hundreds of microservices. This scale is only achievable with containerized cloud-native architecture. Each service is owned by a dedicated team responsible for development, testing, deployment, and production monitoring. This autonomy and alignment enable continuous delivery at scale. Services are designed to fail gracefully, scale independently, and be updated frequently, often dozens of times per day, without causing downtime across the system. But more on that on the next episode.
Before we wrap up, can you maybe tell us what happens when things go wrong? Like, what are the biggest challenges?
The biggest challenge is the distributed system complexity that we have. You are now dealing with network, partial and cascading failures at the same time. Let's touch on three important concepts in distributed systems and microservices architecture: circuit breakers, data consistency, and the saga pattern, for example. As we already mentioned, observability becomes crucial but complex. When a user reports a slow page load, you might need to trace through 8 or more different services to find the bottleneck.
Can you give any final, advice for teams considering this architecture?
Yeah, always start with Monolith. Seriously, get your domain boundaries right first, then break things apart when the monolith becomes too inefficient. When you transition, do it gradually. Invest heavily in automation, monitoring, and team training. The operational complexity is real, but when done right, the agility and scalability gains are transformative.
We've covered a lot of ground today, from monoliths to microservices, from deployment headaches to container bliss, and we got deep into the technical patterns that make all of this work. These concepts are not just theoretical, they are real-world applications that can transform how we build and how we scale our software. In our next episode, we'll explore how DevOps practices and cloud platforms tie everything together, creating the modern software development lifecycle.
Indeed, we will explore how cloud services and DevOps practices come together to enable microservices and containerized architectures, forming the foundaries of the modern tech stack for software development and IT operations.
If you find this episode helpful, make sure to subscribe to From Code to Cloud and share it with your fellow developers. A reminder that if you want to dive deeper into any of the tools or the patterns that we covered today, you'll find detailed blog posts linked in the show notes.
And remember, with great distributed systems comes great responsibility. Start simple, evolve gradually, and always design for failure. See you next time.
Bye.
Bye-bye.